So I want everybody to concentrate because it's one of the trickiest chapters. Okay. So concentrate. If there is any doubt, get it clarified. Now listen. Yes. So in the previous chapter, we have discussed what does optics mean, right? So we know what is optics. Optics is a branch of physics which deals with the study of light, right? What are the two main classifications of optics? One is ray optics. I told you the other name for ray optics. What is it?
Geometric optics.
We call it as geometric optics, right? And here we have wave optics, right? So the other name for wave optics is physical optics. Now the question is, before we saw all these things, as we know, optics is a branch of physics which deals with light. From the 8th chapter, we know that light is an electromagnetic wave. Just give me a minute. Just give me a minute. Charge in my pencil. So now listen. So from the 8th chapter, we know that light is an electromagnetic wave. It is an electromagnetic wave. Here we are using the word wave. So in these two chapters, are we doing wave or something else? So the question is, light is still going to be a wave only. So we studied something called as ray optics, where the wave is being treated like a ray, and now we are calling it as wave optics. So what exactly is the difference between these two chapters? That's what we need to understand, right? So what exactly were we doing in ray optics? Like, why did we divide light as two different things? In one particular part, you're completely dealing it like a ray, though it is a wave. It is still a wave, right? It's an electromagnetic wave. Here also it is wave. Here also it is wave. But in ray optics, we never discussed the concept of wave, because every diagram we drew, we represented only as a ray. A ray is something which travels in a straight line path. We represented it like this. Now why are we calling it as wave optics? I've explained this difference that time. Anybody with the answer?
Sir, when light is very small compared to the dimensions, it is treated as a wave.
When light is small compared to dimensions of what?
Dimensions of other objects.
Okay.
What it is passing through.
It is. See, you cannot say light is small, okay? Because light is something you're able to see.
Wavelength of light, sir.
Wavelength of light.
That is the word you missed. See, you are almost there. Yes. When you say the wavelength of light is very small compared to the objects with which, if it is small compared to the objects with which it is interacting, you will approximate it to a ray. Whereas in this chapter, what is going to happen is the wavelength of light is comparable. Okay, you can compare it with the objects with which it is interacting. Is comparable with objects it is interacting with. Okay, so so I hope these two things are clear, right? So here it is, wavelength is very small. Am I clear with these particular points, with these 2 points?
Yes, sir.
Okay, now see. So the next point that we need to answer is, what exactly are we going to learn? Okay, what exactly are we going to learn in this chapter? So that's what the learning objectives is. After completing this chapter, you will be able to understand the concepts and problems based on certain phenomena like this. One is you will understand what exactly is the wave nature of light. Then we will discuss something called as Eigens Principle. Then we have a concept called as interference, based on which we will discuss about Young's double slit experiment along with its variations. Okay. Then we will discuss about what is diffraction. Then we will see this resolving power and all is actually not there. You will have the concept of polarization. Alone polarization also this year they have removed. So the main concepts we are going to concentrate upon is, first we will understand the wave nature. That is the introduction of this chapter. Then we will understand what exactly this Huygens principle is. Huygens is the name of the scientist, by the way. I call it as Huygens. Some people call it as Hygiene also. Call him as Hygiene. It's up to you. Then we have interference, and there is an experiment which is based on interference, which is called as Young's double slit experiment. And lastly, we have a pattern called as diffraction. Okay. So, why this concept of wave theory actually came into existence is because it could not prove certain phenomena like interference, diffraction, and polarization. Okay. So, I have to explain what this interference is all about. So, I will do a small, I cannot do an exact activity, but I'll try to demonstrate it. Observe. Okay. Are you guys able to see me?
Yes, sir.
Yes, sir.
So one drawback I have is when you do all these experiments, you should not have light. I directly have a window. Okay. See, I just have a light. You're able to see this, right?
Yes, sir.
So this light, so it's like a small torch, and there is an LED light over here. Now we are going to study about its properties only. That's what we are going to concentrate upon. I have a black screen at the back. Now observe, you're able to see a spot, right? You're able to see a spot on the black screen.
Yes, sir.
Right.
Yes.
So now the question is, when the light was actually traveling like this, right? So I'm having my source only here. You're able to see the source. It's a small light. So when the light is coming from this, what should have not happened according to our expectation? Okay, what should have not happened is, if this light was traveling straight, then this particular opening should have traveled in a straight line path, and you should have found a small dot. But when I take it close, you are able to observe the intensity is getting more. Intensity means the brightness. As it is coming away, the intensity is getting decreased. You are able to see the size of the circle is increasing. I'm not sure if it's clear on the other side.
Yes, sir.
Am I
Yes, sir.
right? You're able to see something like this. So there's one thing. Secondly, I have a window here. See, I have a window here. So when the light is coming, right? So I have an opening here. I have an opening here. If the light had traveled in straight line path, what should have happened? What exactly should have happened? So if the light was traveling in a straight line path like this, okay, then if I keep a screen there, then what kind of a pattern am I supposed to observe on the screen? What kind of a pattern do you think will be? If it had traveled straight, what should have happened?
The same straight line, sir.
So you should have found a rectangular shape on the screen, right? For example, I've kept a black screen at the back. You should have found a rectangular screen. Means the thing which is at the back, see, I'm exactly sitting on the end of the window, at the end of the window. So if the light had traveled only along this path, only I should have been visible. Something which is at the back should not have been visible. But what exactly is happening? You are able to see the screen also at the back, right? So what exactly is the light exhibiting is the question. Okay. So when the light is traveling, assume that there is a window. Okay. Unfortunately, I cannot show everything. Assume that there is the window. When the light is coming from back, okay, you're able to see some scattering. See, now it is like this. I blocked it. So what exactly is happening is the rays which are coming from the sun, they're coming from infinite distance. Had this object, then if I keep my, then the light should have traveled like this. But what exactly happens is when the light is hitting this, it will start getting reflected like this, right? So when it is hitting an obstacle, it starts getting bent. You're able to understand this, guys? So it starts getting bent. That is why you're able to see me, actually. That is why when the light is coming, you're able to see me, right? So that is the phenomenon where the light is actually getting bent. Okay, the phenomenon where the light is getting bent when it strikes an obstacle is what is called as diffraction. I can give you a best example for this. For example, you are sitting in a particular room. Okay, let's say you're attending this class. You have closed all your doors and everything, right? But are you people able to hear what others are doing in the other room? Let's say some TV is running or some songs are being listened. Are you people able to hear that sound? Slightly, at least. I'm not saying it's is it completely soundproof?
No, sir. We
No,
can hear.
sir.
Like you're sitting, no, right? You're able to hear something, right? So what exactly is happening? What phenomenon is sound exhibiting? So the sound, once it travels, no, wherever there is an opening, for example, at the bottom of your load, if there is an opening, the sound will travel through it and starts getting bent, and it is coming to your ears. So that is called as diffraction of sound. So diffraction itself means bending of something, and this kind of a phenomenon can be exhibited only by objects which have wave nature, only by physical quantities which have wave nature associated with it. Are you guys able to slightly understand what I'm trying to say? Because
Yes,
diffraction
sir.
is the third concept we are going to discuss. Okay. So what we are going to do is, based on certain arguments, this chapter has actually got built. So let's see what exactly is happening. So the phenomenon of interference, diffraction, and polarization exhibited by light could not be explained on the basis of, there is something called as Newton's corpuscular theory. I'll explain what it is. That is going to be the next subtopic. Okay. So these three phenomena could not be explained with the help of Newton's corpuscular theory. So in 1678, what happened is, Huygens is the first person who proposed that light propagates in the form of waves. Are you guys able to understand? Later came all these Maxwell theory and everything. Later came the electromagnetic waves and everything. See, problem here is, now we see, since everything has got originated, now we have a clarity. Now we are reading about light as an electromagnetic wave. But the concept of electromagnetic wave nature of light came only in the 19th century. But when did this happen? When did this discussion happen? 1678. So that time they didn't have electromagnetic theory to support when somebody told it has wave nature. Okay. So that time Newton was a big scientist. So Newton came up with a theory called as corpuscular theory. Corpuscles means particles. So initially what happened is, Newton proposed saying that light had particle nature associated. Okay. So if it had particle nature associated with it, the theory that he tried to explain is, see, all these things we know today, but imagine at that time they had no base to say. So they just proposed it, and all those things started getting developed. Unless you prove something experimentally, you cannot say that it has a particular nature, right? So what he did is, he explained. So this is Newton's theory. Okay, I'm explaining Newton's corpuscular theory. I'm going to explain this and tell what were the mistakes made by him, due to which were corrected later by Huygens to propose that light had wave nature. You people think and tell me, okay? So what he proposed is, he proposed that light is made up of tiny light and elastic particles called corpuscles. So corpuscles means they are particles, okay, which are emitted by a luminous body. For example, in our case, it's the torchlight. So one more important point he mentioned is, these corpuscles travel with the speed equal to the speed of light in all directions in a straight line and carry energy with them. Okay. So again, when these corpuscles strike the retina of the eye, they produce a sensation of vision. All those things are given. Okay. So with the theory, let me explain how we explain the phenomenon of refraction and reflection. Okay. So let's say when light is made up of tiny particles, let's say one such particle is hitting the surface. Okay. If this is the angle of incidence. So from the basics of ray optics, we know what are the laws of reflection, right? What are the laws of reflection? The angle of incidence is equal to angle of reflection, right? So look at the theory that he framed. What did he say corpuscles are? They are elastic particles. So when there is an elastic oblique collision taking place, where one particle is traveling and hitting the surface, which is at rest. So there is a mirror. We know according to the concept of elastic collisions that the particle will rebound with the same velocity, exactly in the opposite direction, making the same angle. So with this, what he explained is, he told that the angle of incidence is equal to angle of reflection, and the concept of loss of reflection is satisfied. I hope you are able to understand this, right? So what did he use? He used the concept of elastic collision. So remember, there is an oblique collision. Oblique means hitting at some angle. So when this elastic collision is taking place, when it hits the surface, he told it exactly rebounds with the same velocity, making the same angle with respect to the vertical. Are you guys clear with this?
Yes, sir.
Yes, sir.
Okay. Now what he explained with respect to refraction observed. So what is meant by refraction? Refraction is bending of light when it travels from one medium to an. Okay, again, what did he say? Light is made up of tiny elastic particles. So when one of the elastic particle is hitting here, this medium and the second medium, which is on either side of the boundary, has different physical properties associated with it. Accepted? So they have different physical properties. So when it is made up of, when light is a particle, okay. So what will the particles on this side try to do to the particles which have hit the surface? So they have hit the surface, right? What will these particles in the other medium try to do to them? They tend to attract them, right? So we know according to Newton's law of gravitation that the particles get attracted. It's an attractive force, right? So when they're getting attracted, what exactly will happen? The particle which was in the first medium will start experiencing a force, because attraction or repulsion is a force. Okay. Whenever we say anything is experiencing force, listen to the statement carefully. Whenever I say something is experiencing force, can I say that that particular particle is accelerating? Can I say this? Because F is equal to m into a, force experienced by the particle will also accelerate. Are you guys clear with this? So you're able to understand the theory. Okay. When it is going to accelerate, my question is its speed going to increase or decrease? When I say something is accelerating, is the speed increasing or decreasing?
Increase, sir.
Increase.
Yes. So acceleration itself means something, the velocity is increasing with respect to time. But what is the theory we know? When light is traveling from one medium to another, there are two scenarios possible, right? What are the two scenarios? The light can either travel from rarer to denser medium or denser to rarer medium. So when it is traveling from denser to rarer medium, if I say that the particles are accelerating, you will accept it, because in denser medium, the speed of the particles is less compared to the rarer medium. Accepted? Whereas,
Yes, sir.
when you talk about rarer to denser, where is it failing? Where is this theory failing? What should have happened when it is traveling from rarer to denser? Will the particle accelerate or decelerate?
Decelerate.
Decelerate.
It is supposed to decelerate, but according to the theory that he proposed, what happened? It is accelerated. Right? So that's why there is a point also mentioned here. See, the first historic experiment in favor of wave theory was done by Foucault, who in 1850 found experimentally that the velocity of light in denser medium is less than that in the rarer medium, which was contrary to Newton's corpuscular theory. Are you guys able to understand why it failed? But this didn't fail in the 17th century. When was the experiment done? It was done only in 1850. Later, this theory came. But at that time, he proposed it, due to which people started believing that light had what nature? People started believing that's not the fact. What did they believe according to Newton? They believed that it had particle nature associated with it. That is, it had corpuscular. According to the, they started believing that light is made up of corpuscles. Are you able to understand this point? See, though this theory is like, it is not from exam point of view, okay, but you need to understand the story of what exactly Huygens tried to propose, because then you will understand what is this Huygens construction and everything. Am I clear till this point?
Yes, sir.
Yes, sir.
Okay. So that is why, see, don't get confused with this point. Propagation of light in vacuum, laws of reflection and refraction were proved at that time, but it failed to explain the concept of interference, diffraction, and polarization, because all these properties are exhibited only when that particular physical quantity has wave nature associated with it. All these are all these are the properties of wave. Okay. I'm going to the next part. Now listen. Okay. Now we'll start with what exactly is wave optics. Wave optics is the study of wave nature of light. The name itself is suggesting. Interference and diffraction are the two main phenomena giving convincing evidence that light is a wave. Okay. So we are till now we told that light is a wave, but in the previous chapter we dealt it as a ray. So we in this chapter what we need to do is we need to establish some relation between the wave nature and the ray concept. Okay. That is where the concept of wavefronts come into picture. Okay, so I want everyone to write down this definition. So what is a wavefront is the locus of all the points which are vibrating in the same phase of oscillation. So write it down. The locus of all the points which are vibrating in the same phase of oscillation. I will explain what it means. Don't worry about it. Write it down. Okay. So the other definition for wavefront is it is defined as the surface joining the points vibrating in the same phase. So let me explain what it means. Okay. So let's say I have a point source. Sorry, it's not a charge, point source. I showed you a torchlight, right? Let's assume that to be the point source. Now I'm going to show you how exactly the light is going to travel, which is not going to be visible to our eyes. This is the theoretical concept that is running. Okay. So they came up with the concept saying that light is going to travel like this in the form of wavefronts and rays, which we cannot see, obviously, right? So when this is happening, can I say, when you have a point source, okay, when I showed you the LED light, how was it actually ejecting the light? Was it in a straight line path or a circular path or spherical path? What was it actually? What is it you saw on the screen?
Circular.
You saw some circle. It's not conical actually. Okay. So let me explain what exactly happens. We know that when it is a point source, light is going to travel in all the directions. Right? And we know that light is a wave. Right? So I will, for simplicity, I will take the lines to be slightly away. But remember, they are closely packed. So this is one wave. This is another wave. This is another wave. This is another wave. It is going like this, right? So what exactly do you mean by phase of a wave? Phase means the particular angle. So observe what I'm going to do is, if I take this as a phase, okay? If I take this as a phase, then what will be the corresponding phase on the second wave? There is the first wave, there is the second wave. So the corresponding phase on the second wave will also be a similar point. Meaning, this is the phase, this is the point at which the wave is reaching its maximum value, that is its amplitude. Are you guys able to understand this? So if I take all such points on all the waves that I have, and what should I do to them is, if I join everything together, what is the shape that you're getting?
Circle.
It is a circular shape in 2 dimension, but this is going to happen in 3 dimension. So a circle, when it comes to a 3 dimension, how is it going to appear?
Sphere.
Spherical. So light is actually going to travel with light produced due to whom? Light produced due to a point source will travel in the form of what? Will travel in the form of concentric spheres. And these concentric spheres are what are called as wavefronts according to the definition. So what is the, now read the definition, you will understand. Wavefront is a surface joining the points which are vibrating in the same phase. Are you guys able to visualize it? The other best example that I can give you is, you have a still water. Okay, what will happen when you drop stone into a still water? You will find
Ripples.
you will find some ripples around it. Right? You will find a set of concentric circles around it. Means the energy is getting transmitted due to that stone. So stone is also a point-sized object. So due to the point-sized object, how are they traveling actually? They are traveling in the form of ripples, right? Concentric circles. So that will be called as wavefront. Wavefront of what? Of that particular source, of that stone. Wavefront created by the stone in water. This is only for understanding, guys. But here our main concept of discussion is going to be only about light. This is only for you to understand how exactly does it look. But only difference is, in water you will be able to see ripples, in light you will not be able to see. Am I clear till this point? So you might also have a doubt of what you mean by locus. So locus is the shape obtained by joining points. I can give you an example like this. If suppose I ask you to define circle. Okay. So what is the definition of circle? So the definition of circle.
The same distance from a point.
Can you please repeat it? Locus of all points.
That are the same distance from a point.
Very good. Very good. So you have a fixed point called as the center. You take multiple points which are at the same distance, which are equidistant from this fixed point. Then if you join all these points, the shape that you get is a circle. So you can define it like this. Circle is the locus of all points which are equidistant from a fixed point. So that is a concept we use there. Locus means a shape that is obtained. Similarly, when you talk about a straight line is locus of all points which are collinear. Locus of all points which are collinear is what is called as a straight line. Okay, so that is how it is going to be. I hope this point is clear. I want you all to have a clarity about this one, because then I can teach you what is Eigens Principle. Any doubt, please ask. So after wavefront, we need to understand how a wavefront and a ray are associated with each other. Okay, so the direction of propagation of light, that is the ray of light, is always normal to the wavefront. This is a very, very important point, because see, if this is how the wavefront due to a point source is going to be, I have taken one such wavefront. Okay, what is the direction in which the light is actually trying to travel? The light is traveling in this path, in this way. So it is omnidirectional, means it is there in all the directions. Guys, are you able to understand this? So these arrow marks are called as rays, and these dotted lines are called as wavefronts. And how are the rays and the wavefronts with respect to each other? They are always perpendicular to each other. Please make a clear note of it. The direction of propagation of light is always normal to the wavefront. That is, the ray is always normal to the wavefront. So with the hope that these 2 points are clear, I'm going to the next point. Okay. Third, So when you talk about a wavefront, when you say wavefront is also traveling, what is the speed with which it is going to travel? So the wavefront travels with the speed of a wavefront, moves onwards from the source, is called the phase velocity or the wave velocity. It moves with the speed of the light. Okay. Next, the energy travels outwards along straight lines emerging from the source, normally perpendicular to the wavefront, that is along the radius of the spherical wavefront. See, for a spherical wavefront, everything is a radial. So if you observe, the light is traveling along the radial vector. That is what the point says. And these lines are called as the rays. So from this, the main concept I want you to remember is, what is a wavefront? So wavefront is locus of all points which are vibrating the same phase. You know what is a ray? Ray is the arrow mark which is drawn in the direction of energy propagation. And how are rays and wavefronts associated? They are always perpendicular to each other. Right? I hope no doubt. So based on the type of source, how are the wavefronts classified? If you have a point source in your hand and you have a homogeneous medium means the medium is completely made up of only one material, then the wavefront is going to be spherical. I already explained this to you. Okay, this part is the wavefront and arrow marks represent the ray. Clear?
Yes, sir.
Similarly, it is not necessary that you will always have a point source. Sometimes you might have a linear source also. So for a linear source, this is the source, okay? Source S from here to here. For a linear source, if you observe what the wavefront is, the wavefront is going to be a cylindrical shape. It is something similar to how we drew the Gaussian surface in the first chapter. Okay. Next is a small part of the spherical or cylindrical wavefront from the distant source will appear to be plane. So if you have a source which is at infinite distance, okay, when you have a source at infinite distance, the rays at this particular point will be parallel to each other, accepted. That is what we did, no? When you take rays parallel to the principal axis, means the rays are parallel to the principal axis because you concentrate on distant object. When the rays are parallel to each other, then what is the shape the wavefront is going to take? It will be a plane wavefront. Okay. So what I want you to remember is, again, in this chapter, we will be more concerned about spherical wavefronts and plane wavefronts. Okay. With this, the concept of wavefronts and rays is over. Is there any doubt, guys?
No, sir.
No, sir.
Okay. So now I'm proceeding to the next concept. Okay. So concentrate on this. So this is called as Huygens Principle. So what exactly this Huygens Principle is going to do? We understood what is a wavefront, right? So this Huygens Principle will help us to determine the position of a given wavefront at any further time. Means if I have a wavefront now, which is formed due to a point source, let's say this is happening at time t. Okay, I'm interested to find out what exactly is going to happen after time 2t. Then this Huygens Principle will help me to understand where exactly is going to be the second wavefront, which is going to appear after an extra time t. Okay. So for that, there are certain steps to be followed, and those steps are also called as Huygens construction. So concentrate. Okay. If there is any doubt, please let me know. See, this principle is useful for determining the position of a given wavefront at any further time if its present position is known. Okay. So this principle may be stated in three parts. So whatever they have stated in your textbook, they would have even called it as Huygens construction also. Both mean the same, Huygens principle or construction. Okay. So first and foremost important point is, if you have any wavefront that has appeared at some instant t, okay, you have a wavefront. Now, how many points is this wavefront going to have? So how many points will any wavefront have?
Infinite.
You have infinite number of points, right? My question is, if I say this is the first wavefront generated, since we are taking it, see, for understanding purpose, I'm considering a point source. If I take a point source, this point source is the one which is responsible for the first wavefront, accepted? So my question is the wavefront going to stop with this? It is like ripples only. Imagine, no? Is it going to stop with one ripple? No, right?
No, sir.
So the first ripple that has got generated will generate the next ripple by doing what? By spreading the disturbance. That is what a wave is, right? Wave is nothing but spreading of energy by creating some disturbance, right? So every point on the given wavefront may be regarded as the source of the new disturbance. The meaning of this is, please understand this clearly, okay? If I say the second wavefront is getting generated here, then for the second wavefront to get generated, it is not the source S which is going to be responsible, where rather every point on the first wavefront will start acting like a source for whom? For the second wavefront. Similarly, if there is a third wavefront that is getting generated, guys, concentrate. If there is a third wavefront that is getting generated, then who will act as a source with respect to the third wavefront?
Second one.
Every
All the
point on the
points on
second wavefront. All the points on the second, it's not the second wavefront, okay? Every point on the second wavefront will start behaving like a point source for the third wavefront to get generated. So that is the meaning of first point. Okay. Second, the new disturbances, that is, new disturbance means second, third, all these are new disturbances. New disturbances from each point spread out in all directions with the velocity of light in the same manner as the original source does, and these new disturbances are called as secondary wavelets. If you observe the diagram that I put here, you have a point source. Okay, observe this carefully. There are two important words that are there which will confuse you. Listen to it carefully. One is called a secondary wavelet, and the second is called as secondary wavefront. They both are different. Okay, so you need to concentrate to understand what the difference between them. I'm going to repeat the statement. The new disturbances. So new disturbances means new disturbances from each point. There's a very important word. The new disturbances from each point spread out in all directions. So what exactly is going to happen is, first wavefront. On the first wavefront, you have infinite number of points and infinite number of sources. Now, if I take one such source, okay, observe this. If I take one such source, if this is going to act like a point source S dash, okay, I'm repeating it, it is going to act like a point source. Due to a point source, what is going to be the wavefront that is going to get generated?
spherical wavefront.
Yes, that's right. So it is going to be spherical. Is going to be spherical. That is what they're trying to see. So I'm trying to break it into points. Listen, the new disturbance from each point, that each point is what is one of such each points is S dash. Spread out in all directions with what speed? With the velocity of light in that medium. That is very important. Velocity of light in that medium. In the same manner as that of the original source. Here, the original source is S. S dash is a source which we are imagining. Okay, this S dash at this instant will start spreading out in all the directions with how much speed? With speed t. So if I ask you after time t, how much distance it would have covered? We know that distance is equal to speed into time. Accepted? So we know that each disturbance is traveling with the speed of light into after time t. If I take it as t, Then if you take the radius as CT and draw a disturbance, you will get a spherical shaped disturbance called as wavelet. Okay, this dotted lines I've drawn, no, this is not wavefront. Don't get confused. I've seen many people doing this mistake. So I'm repeating it again. Listen to this carefully. Point source. Okay, so point source is, what is this black color line, black color curve? What is this black color curve?
Wavefront.
Wavefront
It is a
for source,
wave
yes.
and very, yes, wavefront. The first wavefront created due to the main source, original source. Okay, and this S dash is one of the points considered on the first wavefront. From S dash with a radius of CT, that is speed multiplied by time after which the wavefront has traveled. With the speed CT, there is a secondary wavelet that is being created. Like this, you will have many such wavelets. Guys, observe. You will have many such wavelets. Of how much radius? The same radius CT. Right? So the radius of this wavelet is CT. Very good. Radius of this wavelet is also CT. Are you guys able to understand this?
Yes, sir.
Yes, sir.
Now comes the question about what is a secondary wavefront? How do I obtain the secondary wavefront? Till now, we spoke only about secondary wavelet. So we have combined the first 2 points. We have come till the stage where we understood that there is something called a secondary wavelet. Now, how to obtain that secondary wavefront is the third point. Listen to it carefully. The surface of tangency to the secondary wavelets in the forward direction at any given time gives the position of the new wavefront at that time. Okay, so let's complete the story. See, source, primary wavefront, secondary wavelet of radius how much? C into T. So what does the third point say? If you take a tangential point to all these secondary wavelets and join them, then this is what is called as what?
Secondary
Secondary
wavefront.
wavefront.
That's it, guys. It's called secondary wavefront. Okay. So that's why this is also called as Huygens construction. So these are the 3 important steps that he has proposed, based on which what we can do is this principle will help us to successfully explain the concept of reflection, refraction, total internal reflection, interference, and diffraction. Okay, but it could not explain the rectilinear propagation of light. Let's not worry about it. Okay. So are you guys clear till this point? So this new wavefront is what is called as secondary wavefront. So I hope the concept, the difference between wavelet and wavefront is strongly registered in your mind. Yes?
Yes, sir.
Yes, sir. So can you give 2 minutes to note it down? Just the diagram.
Yeah, sure, right. I suggest you all to draw this diagram. Okay. So remaining parts I'll upload it in the app. Don't worry about it. But draw this diagram. You need to practice it.
Sir, I have a doubt.
Yeah, tell me.
Sir, do the primary wavefront and the secondary wavefront lie close to each other, sir?
Need not be. Need not be. See, the way I drew it here is like that. See, for example, if I take this as the primary wavefront, right? So due to the main source S. So on this, there are going to be, on this, every point is going to act like a source for the next wavefront, right? So if I take a circle of a bigger radius, maybe I've calculated this after 1 second. Maybe if you calculate it after 2 seconds, it is going to be a bigger radius. So just by looking at the diagram, don't think that they are going to be close to each other. And that is not a question they are going to ask also. So this concept of Huygens principle tells us only that it is going to tell you what is going to be the new wavefront, what is going to be the position of the new wavefront with respect to the already existing wavefront. More amount of time you take, more farther it is away from the existing wavefront. I hope it is clear.
Yes, sir.
Yeah.
Then will they not fade out, sir, after some time?
Yeah, they do. Energy is transferred. No, obviously it has to fade out. But see here, what will happen is, see, I'm telling you again, it is not the way it is going to travel. There is a theory with which they came up. If it is going to fade out, then how is it able to travel for a longer distance? It will not fade out. It's not like the ripples concept. Okay, it is not going to get faded out.
Yes.
Okay, shall I move on to the next concept?
Can you just show the diagram? Sorry, 1 second.
Yeah, sure.
Done, sir.
Yeah. So we have studied laws of reflection and refraction, right? We know what they are. So what are the laws of reflection? The incident ray, reflected ray, and the normal all lie in the same plane, and the angle of incidence is equal to angle of reflection. Right? Now see. So here we are going to prove it. We are going to prove using whose theory? We are going to prove using Huygens theory. So this Huygens theory has, Huygens theory means it's the Huygens construction that I'm trying to talk about. Okay. So for this, see, I want you all to concentrate. Okay, there is a very, very, very tricky concept. I'll try my best to explain it. If there is any doubt, ask me. Okay. Now see. So reflection is exhibited by what kind of objects? Obviously, mirrors. So when you take a mirror, okay, when you take a mirror, what I'm going to do is, I'm going to consider two rays which are incident from infinite distance. Means, how will those rays be with respect to each other?
Parallel.
They are
Parallel.
parallel. So that's what is there. So let AB be the plane. Sorry, okay. I'll come to that. So what I've done is, I've considered a mirror. On that mirror, I've considered two such rays. Right. So these are rays. So and these rays are coming from where?
Infinity.
Infinity, right? So when these rays are coming from infinite distance, with respect to set of parallel rays, what will be the shape of the wavefront?
Planar.
The plane wavefront, okay? And I told you one more important point. What is the angle between a wavefront and any ray?
Perpendicular.
They are perpendicular. Yes, they are perpendicular to each other. That is a very, very important point. Now, what I'm going to do is, see, if I consider a ray which is perpendicular to both the wavefronts, so observe, I'll use a different color, concentrate. Okay. So for a plane wavefront, when you see, wait, I'll show you how I'm visualizing it. So see guys, if this is a plane wavefront, okay, or else I take this one. If this is a plane wavefront, the rays are like this. Okay. So when I turn it like this plane wavefront, how is it going to appear? Observe. Plane wavefront. Okay. Now this is how the rays are hitting. This is the surface. This is the mirror onto which there is a ray coming. So to this ray, the wavefront is like this. What is that you are able to see? Are you able to see the whole rectangle or only the line?
Line.
You are able to see only the line, right? That is what I called it as wavefront. Then how is it with respect to the ray? The ray is going like this and the wavefront is like this. The ray and the wavefront are perpendicular to each other. I hope you are able to see. I hope you are able to visualize it, right?
Yes, yes, sir.
Okay. So what I've drawn here is the incident wavefront. Means you're able to see only the line with respect to it. So this is the incident wavefront. Okay, that is what is given here. See, let A be, I'll use this diagram for support. Let AB be the plane wavefront incident on the plane mirror. Plane mirror what? M1, M2 at angle BA dash I is equal to I, where 1 and 2 are the corresponding incident rays perpendicular to AB. Are you guys clear with this? So 1 and 2 are the incident rays which are perpendicular to whom? Perpendicular to the wavefront AB. What wavefront is it? It is the incident wavefront. It's not the reflected wavefront, guys. Because you do that wavefront for whom? You do it for incident rays. Am I clear with this?
Sir,
Yes.
can you
Okay.
repeat it, sir?
Which point?
Sir, from first, sir. I got confused.
See, it's very simple. You need to first understand that you have taken two rays from infinity. When I say from infinity, they are parallel rays. So to these two rays, what I've done is I've drawn the incident wavefront. That is the first point that I've considered. And we know that the incident wavefront is going to be perpendicular to rays. Are you clear till this point?
Yes, sir.
Now, that is what is in this diagram. So incident ray, there is another incident ray, and this incident wavefront is perpendicular to whom? Both the incident rays. Now, are you clear?
Yes, sir.
So, what will this incident wave? So, according to Huygens principle, what is the first step that Huygens proposed? Every point on the given wavefront will be regarded as a source of new disturbance. Right? Accepted? So, now tell me, I want you to logically think and tell me, out of the ray number 1 and 2, which one is hitting the surface of mirror first?
First one, sir.
Yes, that's right. So it is the first ray that is hitting the surface. So on the first, so due to the first ray, there is an incident wavefront, right? So every point on this incident wavefront will start behaving like what? Will start behaving like
Source of new disturbance.
source for the second source of the new wavefront, right? Now, okay, listen to this carefully. Let's say at t is equal to 0, the first incident ray is hitting the mirror. Okay. Then can I say the second incident ray is traveling, let's say, an extra time t, because see, at t is equal to 0, where was the second incident ray? It was at point B. Right. So it is taking an extra time t to travel how much distance? From B to, let's say, this point A dash. Are you guys able to understand this?
Yes, sir.
Okay. So observe. The first ray has hit the surface. The second ray is still traveling to hit the surface. So the first ray, once it has hit the surface, it will start generating wavefronts. It is like, assume them to be water, okay? So let's say this mirror is water. The first stone has come and hit the water surface. So what will it start doing? It will start producing the ripples. In a similar way, in this case, it is going to start producing the secondary wavefront. Okay. So observe this. Observe this, guys. So when the first ray is hitting the surface, this point is there, no? So this is the first ray. At t is equal to 0 once it has hit. So this is the time I'm taking into reference. So the stone is dropped. What will happen is it will start producing wavefronts like this. Are you able to understand? Which point am I trying to talk about? the point which has hit the surface, this will start. So this is the point on the wavefront also. Observe. This point A belongs to the incident ray as well as the wavefront AB. So on this, if this point is taken, it will start producing what kind of wavefronts? Spherical wavefronts in the forward direction. Imagine them like ripples. Now I am interested to calculate where is this particular wavefront in the extra, after the extra time t for which the second ray has traveled. I'm repeating it again, listen. So once the first ray hits the surface, it starts producing wavefronts. What kind of wavefronts? Spherical wavefronts. Now question is, how much extra time is the second ray traveling or taking before it hits the surface? It takes an extra time I hope that point has got registered. In the extra time t in which the second ray is trying to travel, the first ray would have already started generating spherical wavefronts. So if I take this point A as the center, wait, okay, my charge is over. Just give me a minute. Okay. Now listen. So how many wavefronts will you have after time t? There is going to be only one wavefront, and that wavefront's radius will be how much?
CT.
That's right. That's a perfect answer. So it is CT. So with A as a center, if you cut an arc like this, okay, if you cut a semicircular arc like this, of radius how much? C into T. In the same time CT, how much will be the distance traveled by the second ray before it hits the surface? From here to here, what will be the distance traveled by it? From point, or to put it in simple terms, what will be A dash B? This distance will also be, it will also be CT. So there are two things happening at the same time. What is happening? The first one has generated a wavefront around it of how much radius? CT, and B A dash has traveled CT. Is everyone clear with this? Is everyone clear with this, guys?
Yes, sir.
Right. So, okay. So from
last part again.
Which part?
The CT part.
Yeah, CT part, what is happening is, the first ray at t is equal to 0 has started generating the spherical wavefront. The second ray is still traveling and means it has to cover a distance of how much value? Speed of the light in that medium multiplied with the time it takes to hit the surface. That is C into T. Okay. And around A, with the same radius CT, you have to draw an arc. Actually, you will not draw this big arc. You will take the compass, keep it at the center, and just cut one arc of radius. How much value? CT. So this is going to happen. So what is the name of this, guys? Is this a secondary wavefront or a wavelet?
Wavelet.
It is a wavelet.
Wavelet.
So what we have drawn here is a secondary wavelet. So to the secondary wavelet, from the second point of instance, if you draw a tangent, I'm repeating it again, listen. From the second, for the secondary wavelet, from the second point of incidence, if you draw a tangent, okay, then the tangent is what is going to give you the reflected wavefront. That is a secondary wavefront. Okay. So keeping all these points in mind, I will show you the diagram which is there in the left hand side because it is to the perfect scale. I drew it approximately. Okay. So to conclude, before I explain this, you need to remember the steps. What are the steps to be followed? First, you need to consider two rays which are coming from infinite distance and they are hitting what surface? The reflecting surface, that is a mirror. Okay. So to those two incident rays, we need to draw a plane wavefront. That is called as the incident wavefront. After this, what did we do? In time t, we calculated how much distance the wavefront has got created by the source at point A and how much is the extra distance traveled by dA dash. Okay, are these points clear? So when you draw all these things and draw a tangent to the surface, you will get the reflected wavefront. Is this clear, guys? So AB is what? AB is the incident wavefront. A dash B is what? Is the reflected wavefront. Okay. We know that rays and wavefront are always perpendicular to each other. Okay, rays and wavefront are always perpendicular to each other. If I take this angle as I observe, okay. So with this construction part is over. If I take this angle to be I, okay, then so if I take this angle as I, or 1 minute. Listen, if I take this as I, then how much will this angle be? The red color angle, how much will it be?
R.
It is not R. It is not reflected ray. What is it? It's an incident wavefront.
90.
I told you incident ray and incident. Very good. It is 90 minus I. So 90 minus I means how much will this angle be, guys?
I.
It's, that is why if you see, they have mentioned it here that the incident wavefront is making an angle I. Are you guys able to understand this point? If this is going to be I, okay. So what are if this I, then what are all the triangles that you're able to see? So you're able to see two triangles A, B, A dash and A, B dash, A dash. Are you guys able to see these two triangles?
Yes, sir.
Yes, sir.
Okay. Now see. When you take these two triangles, observe. Angle B is equal to angle B dash is equal to 90 degrees. Accepted.
Yes, sir.
Angle B is equal to angle A dash is equal to 90 degrees and A dash is common, right? A dash is common. Don't look at the theory that is given there. So A dash is common. Accepted. So these 2 points are clear. And the last important point you need to have in your mind is A B dash is same as B A dash. Why? A B dash is equal to B A dash is equal to how much? It is equal to C into T. It is equal to CT because B A dash is extra distance traveled in the time A has created a wavefront of radius AB dash of both values being the same CT, right? So since all the values are going to be, both the triangles are going to be congruent. So when both the triangles are going to be congruent, angle I will be equal to angle R. Okay. So did you guys understand this? So write down this part, don't copy the left hand side.
Can you show the diagram?
I'll try to do one thing. Yeah. See, I know this concept is tricky because you're not the first people who will struggle. What I will do is I will try to record a video with an overhead and try to send it. I'll try to draw with compass and everything. You also repeat the same thing, you will understand it better. Okay. Yeah. Students, I hope you made a note of this. So this is about proving the laws of reflection using the concept of Eigen. So first, it's better you understand this, then we will go to the concept of law of refraction. Okay. So this we'll see it in the next class. You can stop with this. So I want you all to revise all these concepts because then you will understand the next part. Okay. Just wait for a minute, don't leave.